Hey guys, this is the explanation and application 2 assignment. So the first question goes over the vector space R squared is not a subspace of R cubed because R squared is not even a subset of R cubed. The vectors in R cubed all have 3 entries, whereas the vectors in R squared have only 2. So the set H equals S, T, and 0, where S and T are real numbers, is a subset of R cubed that looks and acts like R squared, although it is logically distinct from R squared. So if you look at the figure below, you'll see that H is a subspace of R cubed. So starting off, we need to show that H is a subspace of R cubed. To begin with, we'll need to understand vector subspaces. So what is a subspace? A subspace is of a vector space is a set of vectors that includes the zero vector, is closed under addition, and is closed under scalar multiplication. So we know from the problem statement that we have we need to show that H set is a subspace of R cubed. And the H subset is S, T, and 0, where S and T are real numbers. So step 1 would be to find the zero vector. And the zero vector in R cubed is, as listed, the 0, 0, 0 in the first column. Since S equals 0 and T equals 0 are both real numbers, then we know that the zero vector is in H. So the conclusion is the zero vector is in H. Next step, we need to look and see if it is closed under addition. So we take two vectors in H. We'll call them U and V. U is going to hold S subset 1, T subset 1, and 0, whereas V is going to hold S subset 2, T subset 2, and 0. So if we add those two vectors, U plus V, we would have the S1, T1, 0 plus S2, T2, 0 equals S1 plus S2, T1 plus T2, and 0. And once again, since we know that all the S and T values are real numbers, then we know that that is in H. So conclusion is H is closed under addition. Next, we need to check and see if it's closed under scalar multiplication. So we take any vector in H, we'll call it U, and that's S, T, and 0. We multiply that by a scalar C. So any scalar number, we're just using, in this instance, the letter C to represent that number. We multiply that times ST and 0, and we get CS, CT, 0. Once again, since we know S and T are real numbers, CS and CT are both going to be real numbers, and therefore that matrix is in H. So the conclusion is H is closed under scalar multiplication. The final conclusion on this problem, H contains the zero vector, H is closed under addition, and H is closed under scalar multiplication. Therefore, H is a subspace of R cubed. The key concept to understand with this problem is that a subspace of a vector space is a set of vectors that includes the zero vector, it's closed under addition, and it's closed under scalar multiplication. Some related concepts and examples would be subspaces in R to the n, examples of subspaces in higher dimensions, such as planes and lines through the origin in R cubed. Basis and dimension. We need to understand how to find a basis for a subspace and determining its dimension. We need to understand what the span is. Span is the set of all linear combinations of a given set of vectors, which forms a subspace. And for linear independence, a set of vectors where no vector can be written as a linear combination of the others. All right, so for problem number 2, we need to show that H is not a vector space. In this, we need to understand vector spaces and scalar multiplication. So what this is asking is, what is a vector space? And just from looking in the book, we know that a vector space is a set of vectors that includes the zero vector, it's closed under addition, and it's closed under scalar multiplication. Our problem statement wants us to show that the set H of all points in R squared of the form 3s and 2 plus 5s is not a vector space. To do this, we'll demonstrate this by showing that H is not closed under scalar multiplication. So first we need to define the set H. The set H is defined as H equals 3s and 2 plus 5s. And in this situation, s is a real number. So in the example for s equals 1 would be u equals 3 times 1 and 2 plus 5 times 1, which comes out to a matrix of 3 and 7. So since we're checking for scalar multiplication, we need to take the vector u, which is 3 and 7, from H, and a scalar c equals 2. We multiply that vector by the scalar. So cu equals 2 times 3 and times 7. And when we take that, we get 6 and 14 for our matrix. Now we need to verify closure under scalar multiplication. For 6 and 14 to be in H, it must be of the form 3s and 2 plus 5s for some real number s. So to do this, we just need to set up the equation. We need to verify that 3s equals 6 and 2 plus 5s equals 14. So if we take 6 divided by 3, we get 2, so s equals 2. Then we take 2 plus 5 times 2. 5 times 2 is 10, plus 2 is 12. So we find that 2 plus 5 times 12 equals 12, but not 14. So in this situation, what we find out in our conclusion is that the vector 6, 14 is not of the form 3s and 2 plus 5s. Therefore, H is not closed under scalar multiplication. So our conclusion is that H is not a vector space. The key concept in this problem is that for a set to be a vector space, it must be closed under scalar multiplication. If we're multiplying a vector in the set by a scalar results in a vector outside the set, then the set is not a vector space. Some of the related concepts and examples with vector spaces, the definition is a collection of vectors that can be added together and multiplied by scalars while satisfying certain axioms. Those being closure under addition and scalar multiplication, existence of a zero vector, etc. An example would be r squared, r cubed, and more generally, r to the n power. And the two is subspaces. The definition of a subspace is a subset of a vector space that is itself a vector space under the same operations. An example of that would be the plane through the origin in r cubed, or lines through the origin in r squared. For basis and dimension, a basis is a set of vectors in a vector space that are linearly independent and span the vector space, whereas a dimension is the number of vectors in the basis for the vector space. As you can see in the example in R cubed, the standard basis is 1, 0, 0, 0, 1, 0, and 0, 0, 1, with the dimension being 3. Now span, the definition of that is the set of all linear combinations of a given set of vectors. So for example, the span of 1, 2, and 3, 4 is the set of all the vectors that can be formed as A times matrix 1, 2 plus B times matrix 3, 4 for all real numbers A and B. Finally, linear independence. It's a set of vectors, or a set of vectors is linearly independent if no vector in the set can be written as a linear combination of the others. The vectors 1, 0, and 0, 1 in R squared are linearly independent. Now for the final question, determining if vectors are in null A and column A. For this, we need to understand null space and column space. So a couple key concepts to understand. Null space, or null A, is the set of all vectors x such that AX equals 0. Column space, or col A, this is the set of all possible linear combinations of the columns of A. So our problem statement, we're given matrix A, which equals the following matrix, and then given vectors u and v, and those being what's listed on that slide. Our tasks are to determine if u is in null A, and could u be in column A. Also, we need to determine if v is in column A, and could it be in null A. So step one is to find out if u is in null A. To check if u is in null A, we need to verify if AU equals 0. To compute AU, we take the matrix A times the matrix U. As you can see, doing the calculations for those, we come out with a matrix of 0, -3, 3. Since AU is not equal to 0, we know that U is not in null A. For U to be in column A, it must be a linear combination of the columns of A. However, U has 4 entries, while the columns of A have 3 entries, which makes it impossible. So the conclusion is that U is not in null A and cannot be in column A. Step 2, we need to determine if V is in column A. So to check if V is in column A, we need to see if there exists a vector x such that AX equals V. Set up the augmented matrix and row reduce from this matrix. So if we perform row operations to reduce the augmented matrix to row echelon form, after row reduction we find the following matrix. Since there is no contradiction, V is in column A. But could V be in null A? To be in null A, V must satisfy that AV equals 0. And once again, to compute that, we take AV, which is the matrix A times matrix V. And since A has 4 columns and V has 3 entries, we know that that multiplication is not defined. So therefore, the conclusion is that V cannot be in null A. And our final conclusion is that U is not in null A and cannot be in col A, whereas V is in col A but cannot be in null A. The key concept to keep in mind for this problem is that null A is the set of solutions to AX equals 0, whereas column A is the span of the columns of A. Some related concepts and examples would be that row space, which is the set of all linear combinations of the rows of A. An example of that would be to find the row space of a given matrix. Also, I looked at the rank nullity theorem, definition of that being the dimension of the column space plus the dimension of the null space equals the number of columns. So an example would be to apply the theorem to determine the rank of a matrix. Third, we have basis for null A and column A. The basis for null A is the set of vectors that form the null space, whereas the basis for column A is the set of linear independent columns of A. And linear independence is the definition is that it is a set of vectors where no vector is a linear combination of the others. An example of that being that if we determine if a set of vectors is linearly independent.